2.2 theoretical probability. So in the last lesson, we covered experimental, and now we're going to cover theoretical. So we're going to do a quick recall. Okay, experimental probability, which was covered in 2.1. This is when the results of an actual experiment are used to estimate the probability of events. So what we would do in that case is we would calculate the probability of whatever your desired outcome is, and that will equal the number of successful trials. And I'm calling them trials because you actually did the trial, like you went through the motion of doing the experiment, okay, over the total number of trials. Okay, now theoretical probability is what we're actually going to do in 2.2. This is when the probability of events can be measured based on possible outcomes. So this is the highlight here, possible outcomes. Okay, so in regards to possible outcomes, we're doing this based on an ideal situation where everything's completely fair. Okay, and this has the equation very, very similar. The probability of whatever your desired outcome is the number of successful outcomes divided by the total number of possible outcomes. Okay, we're going to start with a question having to do with a deck of cards. I understand that a deck of cards is a little bit cultural, so you may not have grown up with this. So let me just give you a quick overview. Okay, for any deck of cards, we have the numbers basically 1 to 10. Ace is 1, so ace is the A, and that basically equals like our 1. Okay, so we have ace to 10, then we have jack, queen, king, right? And if you think about like a hierarchy of like royalty, this would be in order, jack, queen, king. Okay, so that's what we do. We also have 4 different suits. Okay, we have, this one's called clubs. This one's called spades. These are called suits. Okay, this one's obviously hearts. And this one's called diamonds. So if you're ever given a situation where you are not very familiar with it, we can still find the probabilities just by looking at either the numbers or the faces. This is like royalty, right? These are called face cards because it literally has somebody's face on it, okay? Or like number cards. Okay, so we can either look at the suits or like the number on the cards, and we can still find the theoretical probability. So a standard deck of cards consists of 52 playing cards. That's what I showed you below, and we'll reference that. Write the theoretical probability of drawing a heart. So the probability of a heart is, we know it's going to be how many hearts. We can even write that number of hearts over total cards. Okay, we already know the total cards is 52. That's not going to change. I'm going to write this underneath. Save space. Okay. Now, how many hearts do we have? So if we take a look at playing cards, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 hearts. So the probability of drawing a heart is 13 out of 52. Okay, and we did this in our 2.0 warm-up, the prerequisite skills. Let's divide both of those by the same number so that we can simplify that to the lowest fraction. Well, 13 is a prime number, so we can only divide both of these by 13, and 52 does divide by 14. or sorry, 13. We get a quarter. So in other words, 1 out of every 4 cards, it's going to be a heart. A quarter of all of the cards is going to be a heart. Now, B, what's the probability of drawing a red king? So we're going to go probability of red king. Okay. This is going to be the number of red kings over the total number of the cards. Okay. So let's scroll down. Red kings. Well, I see 1 red king here, the heart, and 1 red king here, it's the diamond. Okay, we have 4 kings. So this is 2 cards are going to be red kings out of all of the cards. So 2 out of 52 cards will be red kings. So that is the probability, but we can also reduce 2 and 52. Go ahead and divide both by 2, and we get 1 over 26. So the probability of drawing a red king is 1 out of 26. Okay, what's the probability of drawing an ace? So the probability of ace is going to be the number of aces over the total cards. So if we go down here, how many aces do we have? So locate the aces, and we can see that we have 4 of them, right? We have 1 for each suit. So we're going to have a probability of 4 over a total of 52 cards. Okay. And divide both the top and the bottom, the numerator and the denominator, by 4, and we get 1 over 13. Okay, D. What's the probability of not drawing a queen? So this is going to be the probability of not queen. So we're going to calculate the number of not queens over the total cards. So of course it's going to be over 52. So let's take a look at these cards. So we see that we have 4 queens right here. We can either count these directly, or we know there are 52 cards and there are 4 queens, so there are 48 not queens. Okay, the other way of doing this is simply going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so I'm at 20 so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now I'm at 40. 1, 2, 3, 4, 5, 6, 7, 8. 48. Okay, so you can do it the short way, you can do the long way, up to you, whatever you're more comfortable with. Okay, so let's go ahead and divide both of these by 4. 48 divided by 52, or 48 over 52 is the probability, and we can reduce that to 12 over 13. So the probability of not drawing a queen is 12 out of every 13 cards that you draw. E, drawing an ace or a face card. So ace or face. Okay, so what we want to do is we want to calculate the number of aces or faces, okay, all together, over the total number of cards. All right, let's put this in black. Ace or face. Okay, so aces are here. 1, 2, 3, 4. Okay, these are all number cards. Then faces are here. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is 16 out of 52 cards. Okay, just clean that up. So divide both by 4, and we get 4 out of 13. So the probability of drawing an ace or a face card is 4 out of 13. Okay, and then the last one. Drawing a spade, a diamond, or a heart. So probability of spade, diamond, I'm going to put dia, or a heart. Okay, so that means the number of spades, diamonds, or hearts over the total cards. Okay, so how many spades do we have? Well, we know we have 13 of each suit. So there's 13 spades. How many diamonds do we have? 13 diamonds. And how many hearts do we have? 13 hearts. So you could write this as 13 plus 13 plus 13 all over 52. Or simply count them out, 39 over 52. Okay? And we can go ahead and divide that by 13, and we get 3/4. Okay, 3 out of every 4 cards is going to be either a spade, a diamond, or a heart. Example 2, Steve is putting posters up for a concert. He has 12 green posters. Oh, by the way, so when I see information given to me in like a paragraph form, I start listing. Okay, 12 green posters. Okay, we have 7 yellow, 21 blue. Okay, I didn't write out the full words, but GUIB, that's okay. And then 2 red. Okay, and then posters. If Steve randomly chooses a poster to put up first, so say all of these ones are just like in a stack and he just doesn't even pay attention, he just pulls one out. Complete luck, complete chance, probabilities all equal. Okay, what we're going to do is find the theoretical probability of the first poster being green. Okay, so the probability of green is going to be the number of greens over the total number. So here, what I usually do is I put an underline there, and that just kind of means equal, like how many do we have all together? So essentially, if we're doing 12 plus 7 plus 21 plus 2, we're going to calculate how many posters we have all together. And we get 42. So the probability of it being a green one is going to be this 12, because there are 12 green ones. So 12 out of 42. Okay, B. What's the probability that the poster is blue? So probability of blue is going to be the number of blues over the total. So the number of blues is 21 over 42. So going back to these two, if we were to divide these by, I think 12 over 42, even if I divided these both by 2 just to see where it lands me, I get 6 over 21. Now I see that we can divide both these by 3, so I get 2 over 3. Sorry, 2 over 7. 21 divided by 3 is 7. Okay, and 21 over 42, I'm going to divide both of these by 21, and I'm going to get 1/2. Okay, probability of red or yellow is all the reds, the number of reds or yellows over total. Okay, so red is 2, yellow is 7, altogether that's 9 over 42. Okay, I'm going to try to divide both those by 3, and I get 3 over 14. Okay, and the probability of not yellow. Okay, the number of not yellows over the total. So the probability of not yellow is going to be, so not yellow would be 12, and we can add these, 21, which is blue, and then 2 are red. So all of those are not yellow, over a total of 42 posters. So 12 plus 21 plus 2 is 35. Okay, and that's over 42. Okay, both of these divide by 7, and we get 5 over 6. Example 3, coin flipping experiment. So first what we're going to do is create a diagram, a tree diagram, of all possible outcomes of tossing a coin 3 consecutive times. Okay, and tossing a coin 3 consecutive times, this here is our trial. So this happens all at the same time. Okay, another way of thinking of this is tossing 3 coins, right? Because we're going to have 3 outcomes, but we're going to toss 1 coin 3 consecutive times. So what are the possible outcomes on the first toss? Well, you're either going to get a tail or a head. Okay. Coin toss number 2. So after tossing a tail, you can again get a tail, or after tossing a tail, you can then get a head. Okay. And after tossing a head, you can get a tail, and after tossing a head, you can also get a head. Okay, so there's 2 possible outcomes if you're tossing a coin once. There's 4 possible outcomes if you're tossing a coin twice. Tail, 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 head, head, tail, head, head. Now, if you toss that coin the 3rd time, if you get tail, tail, you can now get tail, 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 or tail, tail, head. If you got tail, head, you can now get tail, head, tail, or tail, head, head. Okay, so each of these outcomes is branching off to another head or tail. Okay, you get head, tail, tail, or head, tail, head. Head, head, tail, or head, head, head. And if we count all of these possibilities, 1, 2, 3, 4, 5, 6, 7, 8, we get 8 possibilities. Now, using your possible outcomes, state the theoretical probability of tossing 3 tails. So, how many ways does 3 tails show up? I'm going to put 3T. And that's completely appropriate for a test. So, tails only shows up this one way. Tails, tails, tails. So, this is 1 out of 8 different possibilities. Okay, what's the probability of 2 tails? Okay, 2 tails does not mean 3 tails. It means exactly 2 tails. So, we can roll tails, tails, heads, or we can go tails, heads, then we need another tail. So that's 2 possibilities so far. And then heads, tails, tails. And that's it. 1 down here. So 3 altogether. Okay, so there are, and I'll clean that up, 3 out of 8 different ways to toss 2 tails. Okay, so the probability of 1 head. Okay, so tails, tails, heads, that would be 1 head. And then tails, heads, tails, that's also 1 head. And I'm looking, tails, 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 there's no head. Tails, heads, heads, there's 2 heads, so that doesn't work. So on the top portion, we have 2 outcomes. And then 1 head. So head, tails, tails is one head. Heads, tails, heads doesn't work. Heads, heads, tails doesn't work. Heads, heads, heads doesn't work. So again, we have three. We have three situations where we can have one head. So it's 3 out of 8. Okay, and then what's the probability of 0 tails or 1 tail? Okay, so 0 tails or 1 tail. So tails, tails, tails doesn't work. Tails, tails, anything doesn't work. Okay, so tails, heads, heads would be 1 tail. Tails, heads, tails would be 2, so that doesn't work. Okay, so 0 tail or 1 tail. So heads, tails, tails doesn't work. That's 2 tails, but heads, tails, heads will work because that's only 1 tail. And heads, heads, tails works. That's 1 tail. And heads, heads, heads works. So that's 3 and then 1. I'm going to delete this to keep it clean. So altogether that's 4 out of 8, which is 1/2. Okay, actually thinking about this, so how many ways can we roll 3 tails? Well, if you think about it, you can only do that by rolling tails, tails, tails. What about 2 tails? So we can do tails, tails, heads, tails, heads, tails, or heads, tails, tails. Those are your 3 options. What about 1 head? These are actually the same. Because in order to have 1 head, you need 2 tails. So tails, tails, heads, tails, heads, tails, or heads, tails, tails. Okay? 0 tails would only be heads, heads, heads. And 1 tail would be tail, heads, 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 tails, heads, or heads, heads, tails. That's why it's 4 options. Okay, so what would be the difference between experimental probability and theoretical probability in the above experiment? Okay, so if you think about it, experiments are not 100% like fair / accurate, right? Like whoever's tossing the coin, there may be a flaw, okay? So there may be a flaw in the outcomes will not always align with like theoretical, with, we can say like the perfect experiment, i.e. theoretical probability.